Good day everyone, this is John Kirby Boagas, and together with my group mates, I will be explaining the fundamentals of hypothesis testing, one sample test. I hope that you will listen and enjoy our lecture presentation. Now, let's start first with the fundamentals of hypothesis testing methodology. Ano nga ba isang hypothesis? Ang isang hypothesis, in a simplest way, tinatawag natin itong educated guess. Ito ang mga smart prediction na ginagawa natin based natin na obserbahan na maaari nating i-test if it is right or wrong. Matetest natin ito or mapuprove natin ito gamit ang tinatawag nating hypothesis testing. Ito ay isang statistical tool kung saan pinaput natin into trial ang ating mga assumption if it is right or wrong. Now, ang hypothesis ay maaari maging null or alternative hypothesis. Ang null hypothesis, ito ay isang hypothesis that says that the population parameter is equal to the company specification. So, ang null hypothesis, ito ay mga default assumption natin sa kung ano yung na-obserbahan natin. For example, sa previous chapters, serial filling process, the null hypothesis is that the filling process is working properly, and therefore the mean fill is a 368 gram specification provided by the Oxford Serials. The null hypothesis is stated as H_0 is that mean is equal to 368. No, tatatandaan natin na ang null hypothesis is often one of the status quo and is identified by the symbol H_0. Ngayon, ano naman ang alternative hypothesis? Ang alternative hypothesis is ang kabaliktaran ng null hypothesis. It represents the conclusion reached by rejecting the null hypothesis. No, ang alternative hypothesis, ito yung actual observation natin. Kung kanina walang difference yung nakikita natin, parang default yung assumption natin, dito naman sa null hypothesis, is ito yung statement that we are trying to find evidence. And it assumes that there is a difference or effect sa kung ano yung assumption natin kanina. For example, doon sa serial filling process na sinabi ko kanina, ang alternative hypothesis is stated that H_1 is that mean is not equal to 368. At makikita natin na ang null hypothesis ay kabaliktaran talaga ng alternative hypothesis kasi sinasabi kanina na equal lang yung mean 368, tas dito naman sa alternative hypothesis is kabaliktaran which is not equal to 368. Based sa example kanina, kung ang sampled boxes na tinest natin kanina ay above or below the 368 gram mean, ibig sabihin nun, i-reject natin ang null hypothesis. Meaning to say, we need to stop the production and take whatever action is necessary to correct the problem. Ngayon naman, kung hindi naman siya above or below 368, kung tama naman yung null hypothesis natin, or if the null hypothesis is rejected, you should continue to believe that the process is working correctly and therefore walang corrective action na gagawin. In conclusion, or kung iisipan natin sa pangkalahatan, nire-reject natin ang null hypothesis kung ang evidence nagsasuggest that ang alternative hypothesis ay mas makatotohanan kung ano ang sinabi sa null hypothesis. Kung sinasabi na ito, pero pagdating sa alternative hypothesis iba pala, ibig sabihin we have to reject the null hypothesis. Another example, para mas maintindihan natin, yung example na nasa taas, maaari nyo i-pause at basahin ito, tapos magsistart na lang tayo sa null hypothesis at alternative hypothesis. Okay? Ang null hypothesis sa problem na nasa taas is that the population mean has not changed from its previous value of 4.5 minutes, and this is stated as H_0 is that mean is equal to 4.5 minutes. Now, because the null hypothesis is that the population mean is 4.5 minutes, ang alternative hypothesis is that population mean is not 4.5 minutes. Meaning to say, kabaliktaran siya kung anong sinabi ng null hypothesis, and this is stated as H_1 is that mean is not equal to 4.5. Diba kung nakinig kayo sa sinabi ko kanina, ang null hypothesis at alternative hypothesis ay magkaiba. Kasi kung ano yung sinabi ng null hypothesis, yun ang kabaliktaran ng alternative hypothesis. Now, let's proceed with the critical value of the test statistics. So, it says here na ang logic daw ng hypothesis testing ay nag-i-involve sa pag-determine kung ang null hypothesis ba ay tama based sa data na na-collect natin in the sample. Now, based sa sinabi ko kanina, if there's a large difference between the value of the statistics and the hypothesized value of the population parameter, maaari nating i-conclude or we might conclude that the null hypothesis is false. For example, If the sample mean is 320, you might conclude that the population mean is not 368 because the population mean is very far from the hypothesized value of 368. In such a case, you conclude that there is an unlikely to get a sample mean of 320 if the population mean is really 368. Now, because the sample mean is so different from the hypothesized population mean, it seems more logical to conclude that the population mean is not equal to 368. Therefore, we would reject the null hypothesis. However, it says here that the decision-making process is not always clear out. Ang pag-determine what is very close and what is very different is arbitrary without clear definitions. Hypothesis testing methodology provides a clear definitions for evaluating differences. Furthermore, it enables you to quantify the decision-making process by computing the probability of getting a certain sample result if the null hypothesis is true.
So hello everyone, I am Rico Panya and I'll be discussing the regions of rejection and non-rejection. So first, what is the region of rejection and non-rejection? So in hypothesis testing, the region is the reflection of the area in the distribution where the null hypothesis is rejected. So the region corresponds to the values of statistics that are unlikely in the or under the null hypothesis. It is typically in the tails of this, typically calls the tails of distribution. So the region of non-rejection, or also known as the region of acceptance or acceptance region, is the area where the null hypothesis is not rejected. If the statistics falls under the non-rejection region, it is unlikely, isn't enough evidence to reject the null hypothesis. This regions is determined by significance level or alpha, and there are two types of tailed test. There's the one-tailed test, which it lies only on the left or right tail, depending on the alternatives hypothesis, while the two-tailed test is the region of rejection in both extremes of the distribution. Then there are two types of error, the type 1 and type 2 error. So the type 1 error, also called as the false positive. So in definition, it is the rejection or of true null hypothesis. And in other terms, we can say that in decision making, you think there's a problem when there isn't. That's the false positive. And the type 2 error, or what we call also is false negative, it is the failing to reject the false null hypothesis. In other words, or in other term, we call it the you miss the real problem. So in summary, the type 1 error is risk unnecessary action. So it is a one, also called as overreaction, because you think there's a problem when there is none. And type 2 error or false negative, it is also called as missing the danger or underreaction. So it's either you see the real danger and you didn't even react. Next is the probability of each error. So type 1 error alpha has the probability of rejecting a true null hypothesis. It is denoted by alpha, and it is usually set at 0.05 or 5%. It means that there's a 5% chance of risk making a false positive decision or conclusion. Then type 2 error or beta has the probability of failing to reject a false null hypothesis. It is denoted by beta. A lower beta means a powerful test, and to determine the power, you can use the equation of power is equal to 1 minus beta. So in summary, so alpha is a risk that acting when you shouldn't. So that's why it is called false alarm. while beta is risk of not acting when you should. So it is misdetection.
Next is the hypothesis testing using critical value approach. The critical value approach is a method in hypothesis testing where we compare the test statistic like z-stat to a critical value to decide whether to reject the null hypothesis. This is the value you calculate from your sample data. It shows how far your sample result is from what the null hypothesis claims, measured in terms of standard deviations or z-score. Critical values, these are the cutoff points that define the rejection region and non-rejection region of the normal distribution. They depend on your level of significance like 0.5 or 5%. If the z-stat falls into the rejection region, you reject the null hypothesis. If it falls into the non-rejection region, you fail to reject the null hypothesis. For example, if an alpha is equals to 0.05 and it's a two-tailed test, the critical values are around positive 1.96. If z-stat is beyond positive 1.96, the result is statistically significant, so you reject the null hypothesis. You're comparing your z-stat to a critical z-value that marks the boundary between what's considered a usual result under null hypothesis and an unusual result, leading you to reject the null hypothesis. These boundaries depend on how strict your test is. Sa isang two-tailed na hypothesis test, gamit ang 0.5 level of significance, we divide the 5% sa dalawang dulo ng normal curve. Sa kaliwa at kanan ay merong tag 2.5%. Ibig sabihin kung ang resulta ng test o ng z-stat ay masyadong mababa o masyadong mataas sa negative 1.96 o positive 1.96 na tinatawag na critical values, malaki ang posibilidad na hindi ito dahil tsamba lang. In this case, may sapat na tayong ebidensya para sabihing mali ang null hypothesis, kaya ito ay ating nireject. Next is the hypothesis testing using the p-value approach. If the p-value is small, usually less than 0.05, that means the result is unlikely under the null hypothesis. So we reject the null hypothesis. If the p-value is higher or larger than 0.05, the result could easily happen just by chance. So we do not reject the null hypothesis. In short, a small p-value means there might be something going on worth paying attention to. A large p-value means the result isn't surprising enough to doubt the current situation. Para mas maintindihan ang p-value approach, isipin mo ang halimbawa ng Oxford cereals. Sinusubukan mong alamin kung ang average na laman ng cereal boxes ay eksaktong 368 grams. Pagkatapos ng test, nakuha mo ang test statistic na 1.50. Dahil hindi naman ito sobrang extreme o kakaiba, hindi mo na-reject ang null hypothesis na 368 grams na average. Sa two-tailed test, ang p-value ay nagsasabi kung gaano ka posibleng makuha ang isang resulta na kasing extreme ng 1.50. Pwedeng mas mababa o mas mataas pa. Ayon sa normal distribution table, ang kabuuang posibilidad o ang p-value para dito ay 0.1336. Dahil mas mataas ito sa karaniwang 0.05 na limitasyon, ibig sabihin ay walang sapat na ebidensya para sabihin na mali ang null hypothesis, kaya hindi ito ni-reject. Parang sinasabi ng p-value na oo, medyo kakaiba ang resultang ito pero hindi sapat para sabihing may mali na talaga. In this situation, the average from your sample is 372.5 grams, which is 4.5 grams more than what you expected, the 368 grams. At first, that might seem like a big difference, but when you calculate the p-value, you get 0.1336, which means there's a 13.36 chance of getting a result this far above or below 368 grams, if 368 is really the true average. In simpler terms, yes, 372.5 is a bit higher than 368, but it's not rare or surprising enough to confidently say that something is wrong. That's why you don't reject the idea that the true average is still 368 grams. It's still a reasonable possibility.
Good day everyone. Today I'll be discussing the connection between confidence interval and hypothesis testing. So this chapter, in chapter 8, cover two key parts of statistical inference, the confidence interval and hypothesis testing. So while both are based on the same ideas, they serve different purposes. So Chapter 8 focuses on estimating population values using confidence interval. So this focuses on testing if a population value is less than, equal to, or greater than a specific number. So interestingly, confidence interval can also hint at the same comparison. So for example, in this section, you are tested if the average fill amount was different from 368 grams using a hypothesis test. So confidence interval and hypothesis testing are related but distinct concepts in statistical inference. So understanding both are crucial for making informed decision about the population parameter. So in this slide, you will see the equation below. So instead of using the null hypothesis, you can also use the confidence interval to reach the same conclusion. If the value you're testing, like 368 grams, falls within the interval, you don't reject the null hypothesis. It is not considered unusual. But if it's outside the interval, you reject the null because the value seems unlikely. This approach uses the same data and logic as shown earlier in the equation. So confidence interval can be used as an alternative approach to null hypothesis, providing a range of possible values for the population parameters. So the next topic is, can we ever know the population standard deviation? So the end of this section 8.1 discussed how learning a confidence interval estimation method that required knowing the population standard deviation serve as an effective introduction to the concept of confidence interval. So that passage then revealed that you would unlikely use that procedure for most practical applications for several reasons. Likewise, for most practical applications, you are unlikely to use a hypothesis testing method that requires knowing if you knew the population standard deviation, you would also know the mean and would not need to form a hypothesis about the mean and test that hypothesis. So why study about hypothesis testing that requires that is known? So using such a test make it much easier to explain the fundamentals of hypothesis testing. With a known population standard deviation, you can use the normal distribution and compute the p-values using the tables of the normal distribution. So understanding hypothesis testing with a known population standard deviation provides a foundation for grasping more complex concept in statistical inference, even if it's not commonly used in practice.
Today, I'm going to discuss the critical value approach. In this step, we define what we are testing. We start with a null hypothesis, which assumes that the average sale invoice amount is 120. This represents the current belief or status quo. Next, we state the alternative hypothesis, which suggests that the average is not 120. This means we are checking if there is a significant difference from the expected amount. And there's a two-tailed test, since we are interested in whether the average is either less than or greater than 120. In step 2, we collect a sample of 12 sales invoice to analyze the average amount. Since we don't know the population standard deviation and the sample size is small, we use the t-distribution instead of the normal distribution. We also choose a significant level of 0.05, which means we are willing to accept 5% chance of making a wrong decision by rejecting the null hypothesis when it is actually true. In step 3, since the population standard deviation is unknown and the sample size is small, we apply the t-distribution to perform the hypothesis test. We also assume that the sample data is approximately normal distributed, which is a requirement for using the t-distribution in small samples. The appropriate test statistics for this situation is the t-statistics, which compares the sample mean to the hypothesized population mean. In fourth step, we determine the critical values that help us decide whether to reject the null hypothesis. Since we are using two-tailed tests with a significant level of alpha 0.05 and a sample size of 12, we calculate the degree of freedom. Using the t-distribution table, the critical value for degree of freedom equals 11 at alpha 0.05 are plus minus 2.2010. In fifth step, We have collected random samples of 12 sales values. This data will be used to test the claim about the population mean sales. The average of the 12 value sales is 112.85. The standard deviation, which measures the spread of the data, is 20.80. To determine how far a sample mean is from the hypothesized population mean in terms of standard errors, we calculated the t-statistics. We subtract the hypothesized mean from the sample mean, giving negative 7.15. We divided this by the standard errors. So, sample standard deviation 20.80 divided by the square root of the sample size, which is about 6.004. This result is in a t-statistics of approximately negative 1.19. So what does negative 1.1908 means? This value tells us how many standard errors the sample mean is away from the hypothesized mean. For a two-tailed test with 11 degrees of freedom, the critical t-value at the 5% significance level are approximately plus minus 2.201. If your calculated t-statistics is less than negative 2.201 or greater than 2.201, you rejected the null hypothesis. If your t-statistics is between negative 2.201 and 2.201, you do not reject the null hypothesis. The calculated t-statistics is within the range, so in conclusion, there is not enough evidence to reject the null hypothesis. The samples does not provide strong enough evidence to say the mean sales are different from the 120. In the last step, based on the hypothesis test, the calculated test statistics did not exceed the critical values. Therefore, we do not reject the null hypothesis. There is not enough evidence to say that the mean invoice amount is different from 120. The audit indicates the mean invoice amount remains unchanged.
Hello everyone, so today we're gonna talk about the p-value approach. So this explains how to use the p-value approach in a two-tailed hypothesis test. It shows that after calculating the test statistic, t-stat negative 1.19 and the p-value 0.2588, you compare the p-value to the significance level, or the alpha 0.05. Since 0.2588 is greater than 0.05, you do not reject the null hypothesis. This means there is not enough evidence to conclude that the mean sales invoice amount is different from $120. The p-value tells us that if the true mean is $120, there is a 25.88% chance of getting a sample mean as far from $120 as what was observed, either below $112.85 or above $127.15. So this page clarifies a common misunderstanding about p-values. It is incorrect to say that the p-value is the chance that the null hypothesis is true. The p-value is actually the probability, assuming that the null hypothesis is true, of getting a test statistic as extreme as the one observed. In other words, if the null hypothesis is true, there is a p-value times 100% chance of observing a result as contradictory to the null hypothesis as the sample result.
This topic that we're going to discuss is checking the normality assumption. The t-test is used when the population standard deviation is unknown and is instead estimated using the sample standard deviation for the t-test to be valid. It assumes that the data comes from a random sample drawn from on a normally distributed population. In practical terms, the t-distribution remains a reliable approximation for the sampling distribution of the mean, even if the population is not perfectly normal, as long as the sample size is not too small and the data are not heavily skewed. This makes the t-test a robust tool for inference in many real-world scenarios where perfect normality cannot be guaranteed. To make sure the t-test is appropriate, we need to check whether the sample's data is roughly normally distributed. There are few ways to do this. You can create graphs like histograms, stem and leaf plots, Box plots or normal probability plots to look for signs of skewed data, outliers, or unusual patterns. You can also look at the things like skewness, cortosis, and overall shape of the data to see how closely it matches what we expect from a normal distribution. These methods help us decide if using the t-test is reasonable. In general, if the sample size is not too small, the t-test still works, and even if the data isn't perfectly normal, do not invalidate the use of t-test.
Hello everyone, I am Mr. Kim Cardenas, and for my topic we are going to tackle about the hypothesis testing using the critical value approach, so we can understand how to use critical values to whether reject a null hypothesis. So let's get started. First, what is hypothesis testing? Hypothesis testing is a statistical method to evaluate a claim about a parameter of a population, or a population mean or a proportion. So to get started with the steps of the critical value approach, let's start with an example. So imagine a company that claims that their new cell battery lasts for 10 hours. So to test this, we collect sample data and we use the hypothesis testing to see if the claim supports, if the evidence supports the claim or disproves it. We always start with two hypotheses. First is the null hypothesis, which in our example is the default assumption, which is yes, the battery lasts for 10 hours. And then our second hypothesis is the alternative hypothesis, which is opposing to the null hypothesis, the challenge, which is the battery does not last for 10 hours. So before we collect the data, we choose a significance level, which from our previous discussions is usually 5% or 0.05. So this determines how strict our test will be. So the smaller significance level means that we require stronger evidence to reject the null hypothesis. So next, we compute for the test statistics from the sample data that we have collected. So for this statistics, we use the z-test statistics or z-stats. So the formula for the z-stat is sample mean minus the null hypothesis mean divided by the standard error. So for example, our sample mean is 12, our null hypothesis mean is 10, and our standard error is 2. We get an answer of 1.0, and the larger the absolute value of z-stat is, means the sample result is farther away from the null hypothesis.
The p-value approach is a way to decide whether the results of a study are strong enough to reject a claim. This is what we call the null hypothesis. In this example, the claim is that the average drive-through time is 174.22 seconds. The sample data showed a lower average time of 162.96 seconds. The p-value, which is 0.051, tells us how likely it is to get a result like this if the original claim were true. The p-value approach is a method used in hypothesis testing to determine whether to reject a null hypothesis based on the strength of the evidence in the sample data. It follows 5 key steps. For the step 1, first we state the null hypothesis and the alternative hypothesis. In this example, the null hypothesis claims that the average drive-to service time is 174.22 seconds or more, while the alternative hypothesis suggests that the average service time is less than 174.22 seconds. Step 2. Next, we choose a significance level, which is the maximum acceptable probability of making a wrong decision if we reject the null hypothesis. Here, the significance level is 0.05 or 5%, meaning we are willing to take a 5% risk of being wrong if we reject the null hypothesis. Step 3. We collect sample data and compute the test statistic. In this case, a sample of 25 stores showed an average service time of 162.96 seconds with a standard deviation of 20.2 seconds. Using the t-test formula, the calculated test statistic is negative 2.7871, And the next is step 4. Now we find the p-value, which tells us the probability of getting a test result as extreme as this, assuming the null hypothesis is true. A p-value smaller than our chosen significance level indicates strong evidence against the null hypothesis. In this example, the p-value is 0.0051. Next is step 5. Finally, we compare the p-value to a significance level. Since 0.051 is less than 0.05, we reject the null hypothesis. This means there is a strong evidence that the average drive-through time is actually less than 174.22 seconds. Therefore, we conclude that the current service time is significantly lower, and it is reasonable to consider making changes based on this result. Since 0.051 is smaller than 0.05, it means that the result is very unlikely by chance, so we reject the original claim. This suggests that the average service time is significantly less than 174.22 seconds, and there's enough evidence to support making changes to improve the drive-through process. In simple terms, the p-value approach helps us see whether the results we got are unusual or not. If they are unusual enough or a very small p-value, we decide that our original assumption, the null hypothesis, is likely wrong.
Hello, and welcome to this lecture on hypothesis testing, specifically focusing on the critical z-value approach for proportions. This method is crucial for determining if observed data significantly differs from expected value. So, we'll be using a real-world example to illustrate the process. By the end of this lecture, you'll be able to understand the concept of hypothesis testing for proportions, define null and alternative hypotheses, apply the critical z-value approach to test a hypothesis, and lastly, interpret the results and draw conclusions. So, what is hypothesis testing? Hypothesis testing begins with a question. We start by formulating a null hypothesis, which represents the status quo, and an alternative hypothesis, which suggests a change or difference when we collect data to see if it supports rejecting the null hypothesis in favor of the alternative. So, what is hypothesis testing? Hypothesis testing begins with a question. We start by formulating a null hypothesis, which represents the status quo, and an alternative hypothesis, which suggests a change or difference. We then collect data to see if it supports rejecting the null hypothesis in favor of the alternative. Let's consider a survey conducted for American Express. They wanted to know if the proportion of adults who want internet access to check personal email while on vacation has changed from the previous year. We'll use a significance level of 0.05. This means there's a 5% chance of rejecting the null hypothesis when it's actually true. Since we're looking for any change, we'll conduct a two-tailed test. So, this graph shows the critical z-values that define our rejection regions. If our calculated z-statistic falls outside these regions, we reject the null hypothesis. The survey of 2,000 adults showed that 1,540 wanted internet access for email, giving us a sample proportion of 0.77. Now, we calculate the z-statistic using the following formula. Plugging in our values, we get a z-statistic of approximately 2.0656. Our calculated z-statistic is greater than the critical z-value. Therefore, we reject the null hypothesis. There's a sufficient evidence to suggest that the proportion of adults who want internet access to check personal email while on vacation has changed from the previous year. In summary, we've learned how to apply the critical z-value approach to test a hypothesis about proportions. Remember, this method relies on several assumptions, including a large enough sample size. In future lectures, we'll explore more advanced techniques and other types of hypothesis testing. And by the way, here's one useful tip. Always clearly state your null and alternative hypothesis before starting any hypothesis test. This ensures clarity and helps avoid misinterpretations.
Hello, I will be explaining the p-value approach. So in this section, it's giving a way to decide if something has changed. So instead of using the critical value method, we will use the p-value method. So a p-value method is the probability of getting results as extreme as the one being observed if the null hypothesis were true. So in this case, we got a z-score of positive 2.0656. We will then calculate the p-value based on how extreme this is in both directions. So the p-value that comes out to be is 0.0389. So what will this mean? We will then compare this p-value to our significant level, which is 0.05. Since our p-value is 0.0389, which is greater than 0.05, we can say that this result is statistically significant, so we will then reject the null hypothesis again. In this scenario, a fast food chain wants to know if a new process at the drive-thru helps fill orders more accurately than before. So the big question is, did the new process actually improve things, or it's just a random luck? So we will find out if the proportion of correct orders has increased from 85%. So we will set up two hypotheses, which is the new process is not better, or it's still 85% or less accurate, and the second one is an alternative, which the new process is better or more than 85% accurate. So we will calculate the sample proportion, which 94 divided by 100 equals to 0.94. So as we test a 1% significance level or 0.01, which is very strict, there are two ways to decide. So the first one is critical value method, which if z is greater than 2.33, we will reject the null, or if our z equals to 2.52, so we will reject the null again. So the second one is the p-value method. We find the p-value for z equals 2.52, or it's 0.0059. Since 0.0059 is less than 0.01, we again reject the null. That's all.
As for the ethical issues, may mga ethical problems na nag-a-arise sa paggawa ng hypothetical testing. Ito ay ang involvement ng pagmanipula ng process, affecting areas like human subjects, data collection, test type, significance level, data handling, and reporting of results. And researchers must avoid these to maintain integrity. And that ends our presentation. Thank you so much for listening, and I hope that you learned something.